All right, so when we left last term, we ended talking about aromatic systems, and we talked quite a bit about how to identify aromatic systems, how to name them, and some of the reactions at the benzylic position and Birch reduction, things like that. Well, this time what we're going to do is we're going to actually look at reactions that occur on aromatic carbons. And in particular, these are called aromatic substitution reactions. And there's a couple different types that we'll talk about. The first type that we're going to talk about is electrophilic aromatic substitution. And it's kind of a strange thing when we think about it. So if we said last term, if we have benzene and we react it with bromine, what will happen? So nothing. Why will nothing happen? Because why? I heard somebody say because it's aromatic. And if you remember, we said that aromatic compounds have remarkable stability. If we think about the double bonds here, they're not like a normal alkene, right? Because they delocalize around the ring. They're not a true double bond. They're kind of between a single bond and a double bond. So in this case, if we try to react this with bromine, we get absolutely no reaction occurring. The interesting thing that was observed was, let's take benzene again. This time I'm going to react it with bromine and put in some iron. If we do this, we can actually create bromobenzene, right? Pretty strange, right? Is this our normal electrophilic addition of an alkene? No, if it were our electrophilic addition of our alkene, what we would expect would be that we'd have one bromine here, the other bromine would be anti, and we'd also get an enantiomer. In the bottom example where we've added iron, we're only installing one bromine, and what's special about it? If we look at the top one, is it aromatic? No, we've broken aromaticity in the top one. The bottom one, it's still aromatic. In the top one, we said we broken aromaticity. So this bottom reaction, we're actually able to do an electrophilic addition without breaking the aromaticity of a molecule. But in doing that, we can only install one halogen into this. You have a question, Daniel? Yeah, we're definitely going to go through these mechanisms. All right, so let's start with just a very, very general mechanism. And I know I showed bromine here. We'll go through the mechanism for halogens here in a minute, but I just want to show the overall very vague generic mechanism. So if we look at the general mechanism, we've got benzene. Benzene's got pi bonds in them. Are pi bonds nucleophiles or electrophiles? Nucleophiles, right? So we could say, all right, we've got benzene. Benzene's a nucleophile. And then what we're doing is we have to react this with some sort of electrophile. So I'm just going to call this generic E+. Right? So if we do our arrow pushing, we can say, all right, the nucleophile that's a pi bond will attack our electrophile. Oh. Shoot. Sorry. There we go. And I'm going to draw in these couple of hydrogens here just to emphasize where the positive charge is. Now we've got a positive charge on the carbon that's adjacent. Shoot. This shouldn't be ethyl, that should just be E. There we go. All right, so we've got a positive charge on the carbon that's adjacent to the carbon where the electrophile added in, right? Because if we look at benzene, there's only one hydrogen on each of those carbons. So the next step is that we have to get back to being aromatic, because right here, we've broken aromaticity. This is a very, very unstable compound, right? Would be much, much happier being aromatic and not having a positive charge. And so this compound actually has a very particular name. It's either called a sigma complex, or oftentimes it's called an rhenium ion. The key is we're going through an intermediate that's very, very unstable. It's got broken aromaticity and it's a carbocation. So in the next step, what we do is we have some sort of generic base, and I'll call that B with a lone pair. This will come grab that proton, clamp down, and it will restore the aromaticity to this compound. And it will create our conjugate acid. So restored aromaticity. What's special about the carbocation in the top right-hand corner? It does have resonance, so we can actually draw resonance structures for that. So it is very high energy, meaning that it's not aromatic, but it is stabilized through resonance. So these reactions are very, very useful for installing an electrophile. The key is we have to have a very good electrophile. If we use a generic electrophile like Br2, bromine, it's not going to do anything. We have to convert bromine into a super strong electrophile somehow. And we're going to talk quite a bit about how to do that and the overall mechanisms for some of these new reactions. All right, so let's switch gears and talk specifically about halogenation reactions. So we already said if we have bromine and we sprinkle in iron, we can install a bromine on a benzene ring directly. And there's two main types of halogenation reactions. The two we'll most commonly see are bromination. So if you have benzene, you can install a bromine. And there's chlorination. So with bromination, we obviously would need Br2. And then we can also add in the iron. Specifically, what we'll do is we'll add in iron tribromide, so FeBr3. The interesting thing with these reactions, I'll put a little asterisk here, is if you react two equivalents of iron with 3 equivalents of bromine, you'll just make 2 equivalents of iron tribromide. So that's how we're getting our iron tribromide here. Is you can actually just do this with iron as well, but it's oftentimes much easier just to buy iron tribromide. With chlorine, the reagents are slightly different. You do this with Cl2, and then you do aluminum trichloride there. In either case, iron and aluminum are excellent Lewis acids. They want electrons very badly. So in this case, it'll turn bromine or chlorine into a very good electrophile. And we'll talk a little bit more about why that works well.
You're forgetting the 2 on your iron plus your bromine on the bottom, which should be Br2 on your reactant side.
Oh, thank you. Br2, I was looking up above. Good catch. All right, so the question is, how can we interact a Lewis acid with bromine or chlorine in order to make them a really good electrophile? So let's start with the mechanism for bromination. All right, so the first step, we've got this bromine floating around in solution. And I'm going to go old school and draw all of our lone pairs. Oh. Okay. So we've got bromine, and then we've got iron tribromide that we just formed. And I'm going to draw iron tribromide kind of on its side. And then if we think about this, iron tribromide has this big empty p orbital sticking straight up and straight down, right? Which means if it's got an empty p orbital, it really, really wants electrons. And where will those electrons come from? Just directly from bromine, right? So bromine is one of those weird molecules where it can act as both an electrophile and a nucleophile. So in this case, it's acting as a nucleophile, donating electrons to the empty p orbital. And so when it does this, we've now got this kind of goofy looking complex here. And the iron becomes tetrahedral. And in this case, the iron has a negative charge, and the bromine has a positive charge, right? So we went from bromine, which is a moderately strong electrophile, to a super, oh, shoot, let me erase this, to a super strong electrophile. That bromine in particular is not very happy with that positive charge, right? It's an electronegative atom, which means that it's going to be pulling a huge amount of electron density away from its neighbors. In particular, that bromine on the end right here is going to be very, very electrophilic. It wants to pop off to alleviate that positive charge on that bromine. So now we've turned bromine from a moderately strong electrophile into a super strong electrophile. So if we react this with benzene, we said that benzene can be a pretty good nucleophile. And so what it will do is have one of these pi bonds come up, attack that bromine, kick off electrons to that bromine with the positive charge. And now we end up forming that rhenium ion I was talking about. So let me do this over here. Sorry, guys. Got Br and H. And we've got a hydrogen here, positive charge there, and our pi bonds. And then we also have our leaving group. And the iron still has a negative charge. No electrons have moved to it or away from it, so it's still got a negative charge. Iron's not very happy with that negative charge right now, so it can actually use one of those bromines that's attached to it as a weak base. And so what will happen is one of these bonds will break, come over, grab this proton, clamp down, and we can restore aromaticity. And then we get our regenerated iron tribromide catalyst. So in the end, we can very easily brominate a benzene ring by using iron tribromide and bromine. The other interesting thing, too, that I wanted to bring up is I'll put an asterisk next to that iron. Occasionally, you might see this done with aluminum tribromide. In either case, they're both good Lewis acids. You can use aluminum or iron tribromide. So can be AlBr3. Either of those will work well for this reaction. Are there any questions for the overall reaction mechanism? We're going to kind of beat this mechanism into the ground over this chapter because we're going to see it in a bunch of different iterations. It's just, we've got to see it over and over again for it to really click. Otherwise, it kind of looks like Greek at first. All right, do you guys want to see the mechanism for chlorination?
Is it the same?
It's very, very similar, so maybe I'll speed through the chlorination mechanism here really quick. All right, so for chlorination, we end up having Cl, Cl, and in this case we use aluminum trichloride. So we've got Al, Cl, Cl, Cl. I'll draw on my p orbital just to be thorough. And then we said one of these lone pairs could hop into that p orbital. And our aluminum has a negative charge. This chlorine has a positive charge. So it's very, very similar to the reaction we saw with bromine. We're just using aluminum trichloride and chlorine instead of bromine and iron tribromide. All right, in the next step, we again react this with benzene. And benzene will attack this terminal chlorine here, dump electrons onto the chlorine with the positive charge. And now we've got hydrogen here, chlorine here, positive charge, and then we've got our aluminum tetrachloride. I'm not going to draw geometry there, but it should be tetrahedral. This aluminum has a negative charge. One of these chlorines will pop off, grab this hydrogen, clamp down, restore aromaticity to the molecule, and regenerate our aluminum trichloride catalyst. So a very, very similar mechanism. We'll see aluminum trichloride with a couple other reactions too, because it is such an awesome Lewis acid. It loves taking electrons from other things. All right, so these are really useful reactions for installing halogens onto benzene. And what can we do with a halogenated compound that's so useful? Grignard reagent, right? So for example, let's say we've got bromobenzene. We can throw in magnesium metal there. The magnesium will insert between the bromine and the carbon bond, and all of a sudden we turn this into a really good nucleophile. So we can append aromatic rings onto other molecules very, very easily using this method. So halogenated aromatic systems are very common intermediates in synthesis because they're so versatile. You can use them to create a whole bunch of different useful compounds. All right, let's do another one.
So the product is the same except for it has like chlorine attached to it?
Exactly. It's the same product, but just with chlorine. You can do it with iodine too, with copper iodide, but it's not as common. And the reason behind that is that aromatic carbon iodine bonds are actually really, really weak and tend to pop off and degrade over time. And so in our book, at least, they choose to focus primarily on installing bromines and chlorines. If you go on and take organometallic chemistry, you'll learn a lot more about iodination, but it typically is done a little differently. All right, sulfonation is actually a really cool process. So the overall mechanism for sulfonation is a little bit different. Same general reaction. But we use something called fuming sulfuric acid. And when we do this, we can install a sulfonate group. And a sulfonate group looks a lot like this. So sulfur doesn't follow the octet rule very easily. It's happy violating it. But the question is, what's fuming sulfuric acid and how is it different from regular sulfuric acid? Does it mean it's bubbling? Is something coming out of it? I was very unclear on this until I took organic chemistry. Fuming sulfuric acid is something different. It has sulfur trioxide dissolved in it. So it has SO3 dissolved in it. And in particular, if you think about SO3, it's got sulfur that's double bonded to 2 oxygens. The weird thing about this is these pi bonds are really, really weak pi bonds. Some people don't even draw them as double bonds because they don't think that it's very accurately represented as a double bond. It's more like a single bond, and the reason is if we think about a sulfur-oxygen double bond, it's going to be the same as saying a sulfur-oxygen bond where the oxygen's negative and the sulfur is positive. Right? So you can draw it as a double bond, or you can draw it as a single bond where you're actually dumping that charge onto the oxygen. So in this case, if we're looking at the sulfur here, this is a very good electrophile, right? Oh, I keep on doing ET. So that sulfur really, really wants electrons. Some people might even draw that sulfur trioxide as being an ionic compound, but you can draw it all as being double bonds. So the mechanism for this reaction involves using the sulfur trioxide as an electrophile, not the sulfuric acid, and that's something that confuses a lot of people. Is the sulfuric acid is essentially just the solvent in this reaction. It's not doing anything more than that. All right, so the mechanism starts with benzene again. And we're going to react this with our sulfur trioxide. So this double bond will attack that sulfur, and we can have it kick up electrons onto this oxygen. So this oxygen has a negative charge. The neighboring position over here is left with a positive charge. So we've added that sulfur trioxide directly onto the benzene ring. The kind of screwy thing with this reaction that bugged me for a long time was sulfuric acid is a very, very strong acid, right? Which means it's an incredibly weak base. So if we think about the conjugate base of sulfuric acid, it would be this guy. And when I did this for the first time, it felt wrong to say, all right, the conjugate base of sulfuric acid is going to grab a proton back. That doesn't make any sense. But what's the main driving force? Restoring aromaticity is a huge thing here, right? So in this intermediate step, it's not aromatic, which means it desperately wants to become aromatic. It wants to restore aromaticity. So sulfuric acid, the conjugate base, is a super, super weak base, but in this case, it doesn't matter. The driving force is restoring aromaticity to that benzene ring. So when we do this, we now get close to being done. But we still got a negative charge on that oxygen. What do you think will happen next? Yeah, it'll grab a proton from sulfuric acid. We've got a really strong acid around, so it'll just grab a proton from there. So we'll do our arrow pushing, showing that proton transfer. and we end up with our final product. The interesting thing with this reaction is that the product itself isn't that valuable. Oftentimes these aren't as highly desirable molecules. But what we'll see later in this chapter is that this reaction is actually reversible. So we can go from this final product down here straight back to the beginning by using dilute sulfuric acid. And we'll talk about why this is so useful, but I'll give you guys kind of a preview. You can use this electron withdrawing group to actually direct reactions on other sides of the benzene ring and then pop it off at the very end. So what we call this is using a directing group in order to favor reactant installing at one regiochemical position. It's a really valuable synthetic technique, so it is completely reversible in this reaction. Does that make sense for sulfonation? We're going to spend a lot of time talking about directing groups and planning synthesis for this chapter too. All right, the next one. It's one of my favorite reactions because I have so many. And this is nitration. So let's say we've got let me just go straight to the product and then I'll fill in the reagents. Let's say we've got benzene and we want to install a nitro group. So we're making nitrobenzene. We can react this with nitric acid, which is HNO3, and sulfuric acid, and get a nitro group to install very, very easily. The cool thing with this reaction, which is why it was so popular, is let's take this guy. What's the name of that parent compound? Toluene. Okay, and we're going to react this with HNO3, H2SO4, and we're going to do this in excess. So we are actually going to install more than one nitro group. You'll get a nitro group installed in the ortho and para positions on this ring. Why is this reaction beneficial? Or I guess, depending on your view.
You can blow stuff up.
You can blow stuff up, right? So let me actually slide this over. So I'm TNT. I'm dynamite. All right. So TNT, if you think about it, you've got a lot of nitro groups on here. These nitro groups very much want to become gas. So anytime you do a transition from a solid or a liquid to a gas, they tend to be very, very explosive. So the most explosive compounds in the world have tons and tons of nitro groups on them. The military-grade explosives that are used, I think one of them has 6 nitro groups on them. So the higher the nitrogen to carbon ratio is, the more explosive these compounds tend to be. So nitration is often used in explosives chemistry. All right, so let's take a look at the mechanism here. All right, the mechanism starts out a little bit differently. So if we look at nitric acid, I'm going to draw in lone pairs here. We've got a negative charge on that oxygen, and we've got a positive charge on the nitrogen, right? So go back to Gen Chem Lewis dot structures. And then we're also running this in sulfuric acid. So the first step for this reaction is just an acid-base proton transfer. Those are usually the quickest reactions in chemistry. And the thing that's a little bit confusing is it's not the oxygen with the negative charge that's attacking, It's actually the oxygen that's the alcohol grabbing the proton on sulfuric acid and then dumping electrons onto that oxygen. And the reason is we can turn that alcohol into a really, really good leaving group by protonating it. So I'm just going to call this OH2 plus. This nitrogen has a plus. Oxygen's negative. And now we've got an awesome leaving group. So I'll call that good leaving group. Next step, we take the lone pair from the oxygen with the negative charge, dump it down, and we just kick off our leaving group. So now we've got a nitrogen with a positive charge, and we've made water. So if you think about it, is that nitrogen going to be a decent electrophile, a good electrophile? What's it going to do? It's going to be a great electrophile. Nitrogen's electronegative. It doesn't want that positive charge. It would much, much rather be neutral. So in this case, we formed what's called a nitronium ion. And the nitronium ion is a super good electrophile. That nitrogen with the positive charge is great. All right, so now we've created our good electrophile. Nitric acid on its own wasn't a great electrophile, but by popping off one of those water molecules, we've turned it into a great electrophile. So we'll have this react with benzene. So we'll draw the pi bond coming over, attacking that nitrogen. And we don't want to have a pentavalent nitrogen, so we're going to dump some of these electrons over to the oxygen. So I've got a nitrogen now that's single bonded to one oxygen, double bonded to the other. And we've got a nitrogen with a positive charge there. We finish drawing everything in. And then we also can't forget about the water that's also floating around, so I'll draw the water in over here. So the interesting thing with the nitro group that some people forget is if you look at the nitro group, it's got a negative charge on the oxygen, a positive charge on the nitrogen. What about this other oxygen on the nitro group? Does it have no charge? Yeah, the interesting thing is negative charge on the other oxygen has resonance where it can dump down and transfer that negative charge over to the other oxygen. So it's not that one oxygen has a negative charge or the other one has a negative charge, it's that they share the negative charge and that the nitrogen's positive. So this is a weird Zwitter ion where the negative charge is delocalized across two atoms and the positive charge is on the nitrogen itself. All right, what do you guys think the next step is? Restore aromaticity. So like I said, this is kind of like beating a dead horse a little bit. You can take the oxygen on the water, have that be a weak base, clamp down, and you end up with your new nitrobenzene. Plus, you make some acid that can be reused in the reaction. So it's a pretty straightforward reaction, just like some of the other ones. We'll see some more of these mechanisms tomorrow. But just like with the last reaction where I said sulfonations can be used as directing groups, installing bromines can be used to make Grignard reagents, this one's also very useful because there's another reaction we can do with nitro groups that we haven't quite seen yet. Oh, yeah, thank you. It can also be used to make amines. So let's say we've got our benzene. We said we can easily make nitrobenzene using nitric acid and sulfuric acid. The cool thing is we can take this all the way to an amine. What's this compound called? Aniline. So we've, oops, sorry, that should be NH2. So we can make aniline. And in order to do this, we actually have to reduce the nitrogen there. And the easiest way to do this is you just treat it with HCl and iron or zinc. And so we can go directly from a nitro group to an aniline pretty easily that way. And again, this kind of goes back to the idea of directing groups. If we think about a nitro group, is that electron withdrawing or donating? It's withdrawing. What about an amino group? It's donating, which is weird to think about. We would say, well, this bond's polarized. Nitrogen's electronegative, so there's a dipole going towards the nitrogen. But there's also resonance, right? The lone pair on the aniline can actually get dumped down into the ring and delocalize that lone pair all the way through the aromatic ring system. With the nitro group, it can only pull electrons out. It can't pull electrons in. So in this case, we can convert between electron donating and withdrawing groups pretty easily by converting from a nitro group to an aniline. So I think we're going to hold off there. Tomorrow we'll talk about Friedel-Crafts alkylation and acylation.